Hi, my name is Michael Lavara, and welcome to Paint and Materials Effect Testing Part 5, where I compare 100 low lead and G100UL on paint and materials. First, I wanted to take a moment to address some rumors and clarify why I've been performing this testing over the last several months. You see, I have a keen interest in this topic because the Cessna 182 behind me that I operate requires a 100-octane avgas fuel and is powered by a motor modified by STC called the PPONC 0470-50, or now a North Point XP470. Dating back to January 2022, I've been unable to fill this aircraft here at my home base with 100-octane avgas because Santa Clara County banned the sale of 100 low lead. I became educated on the unleaded fuel topic because I was part of a Part 16 complaint with AOPA against Santa Clara County. The FAA recently ruled on this complaint, noting that Santa Clara County violated its grant assurances and also discriminated against aircraft that required the 100-octane avgas. Based on issues aircraft were having at Reed Hillview and Watsonville after the rollout of G100UL last November, I decided to see if I could reproduce some of these issues being noted in the field. And I can tell you that I never imagined that it would lead to this series of video and the depth of testing. First, I respect the work GAMI has in industry, from their fuel injectors to the development of this fuel. However, some of the issues that have been noted here has me and others concerned, rightfully so. At the core, I just want fuel that is safe to operate and will not damage my aircraft. In this video, I cover some recent news in industry and introduce you to new aircraft and their reported adverse experiences with G100UL. Lastly, I dive deeper into O-rings, and I bench tested Cessna 400 series twin aircraft fuel selectors, where I believe that I've identified a condition that could lead to a potential safety of flight issue. For those who doubt my motives or are skeptical of the testing, I ask you to have an open mind as I present to you these new observations. You'll see why I titled this video, Shuttle Me O-Ring, Beyond My Limits. And since I was recently referred to in a YouTube video as Mike the Mechanic, I wanted to restate my background a little bit for those who hadn't watched the previous videos. I have an electrical engineering degree. I was introduced to aviation with RC aircraft when I was young, and I'm based at Reed Hillview, flying several GA aircraft regularly. I have a few aircraft ratings along with getting my AMP based on experience several years ago. I spent 15 years supplying telemetry systems to the Reno Air Races and crewing on several gold-winning unlimited teams. And my day job is in flight test, both manned and unmanned. If you find yourself here for the first time, there are more videos in this subject in my channel. So what's in this video? The FAA recently put out a special airworthiness information bulletin on unleaded fuels. I'll discuss the Part 16 investigation and the director's determination related to Santa Clara County, and along with that, the STC applicability to my own Cessna. Eagle gave an update on consensus standards. I'll talk about some affected aircraft, both new and updates on old ones, discuss the GAMI fuel spec, dig further into O-rings and related swelling with the fuel, and lastly, I'll showcase some Cessna 400 series fuel selector observations that I think will raise some eyebrows. On March 28th, the FAA issued an SAIB, better known as a Special Airworthiness Information Bulletin. The FAA is seeking input from users who've used unleaded fuels of all types, and they ask that people submit their experience via an email address listed in the bulletin. I encourage anyone who's used an unleaded fuel of any type to report their experiences with the fuel to the FAA. As I alluded to in the introduction, AOPA filed a Part 16 complaint against Santa Clara County for their ban of 100 low lead sales. Recently, the FAA issued a director's determination on March 24th. The determination stated that Santa Clara County violated some of its grant assurances and discriminated against aircraft that required a 100-octane avgas. In response, the county requested an extension of time in order to put a corrective action plan together. However, I just learned that the county filed an appeal of the director's determination. The bottom line out of all of this? If you sign on the dotted line and take money from the government, you have to live up to your end of the bargain and hold to your grant assurance obligations. In the beginning of the video, I introduced my Cessna 182 that has an engine modified by STC. Aviation Consumer covered some of my testing a few months ago, noting something that a few people had real public knowledge of. That is, a declaration that I had filed in the Part 16 complaint, stating that my aircraft's engine, as modified, was not listed on the STC.
With the exception of later model 182s that use Lycomings, older 182s use Continental 0470s, the U, R, or S model. Installed on my 182 is the 0470-50. It's actually built from a 520 core, as the STC allows two variants, one from a 470 core or a 520 core. The engine as installed on my 182 is essentially a TSIO 520C, with the turbocharger and injection system removed, and the added installation of an 0470 induction system oil pan and carburetor. What I want to point out is the plain reading of the STC from GAMI states that when there are multiple engines listed in the TCDS for the same make model aircraft, verify that the engine installed on your aircraft is also listed on the corresponding G100UL AML. The TSIO 520C is not on the TCDS for my Cessna 182, nor is the 0470-50 listed anywhere on the G100UL avgas AML. This leads me to believe that it's necessary to get a field approval for the application of this fuel to my modified engine. And given some users were reporting adverse effects with G100UL last fall, I decided it was prudent to start testing the fuel before I potentially applied for a field approval on my engine and aircraft combination. I also wrote Aviation Consumer back in February regarding their article, and I have yet to hear back. I do feel like proper reporting seeks to look at both sides of the issue, and not just be fed from one source. In March, EGLE, short for Eliminate Aviation Gas-Leaded Emissions, put out an update on their series of Clearing the Air, How Unleaded Aviation Fuel is Gaining Approval, Part 3. This one discusses the role of industry consensus standards in the approval and use of unleaded aviation fuel. I've included the link for this down in the video description below. It's worth a look. A few interesting videos came out on YouTube from Sun and Fun. The first is where George Brawley, head of engineering for GAMI, in response to a question about my tests, actually admits that paint can be affected in the manner I'm presenting, especially when the fuel comes under the edges of paint and then starts to deteriorate. This is exactly what I've been saying for the past several months, and is contrary to the earlier statements where they stated G100UL avgas is not a threat to normal aircraft paint. The original upload of the Sun and Fun Forum Part 3 from GAMI had some off-the-cuff remarks about my credibility, but has since been deleted and uploaded with the new version I referenced. However, I'll say it's encouraging to see them admit that G100UL may affect paint in the manner that I've been presenting. And I'm still looking for all the damage of 100 low-lead affected aircraft on the ramp from this elusive high-toluene 100 low-lead blend. At Sun and Fun, Jeff Simon from Social Flight interviewed Kurt from Eagle Fuel Cells. Kurt had some interesting insights from his years of material compatibility testing with his bladders, and it's definitely worth listening to this on Social Flight's YouTube channel. Perusing Eagle Fuel Cell's website, there's some commentary on materials compatibility with newer fuels. They're stating that fuel cell longevity will be changing with the new unleaded fuels, and materials are already changing for it. Noted though, they say the chemicals are very hard on existing materials, especially the components that are over 20 years old. As been noted previously, GAMI sought out their own fuel specification in lieu of an ASTM consensus standard spec. These specifications are comprehensive, and one of the elements of this is actually the color of the fuel. One of the notable things I've seen is that G100UL, when left exposed to ambient light, tends to darken. Have a look at the two jars, second and third from left, notably the third one, which is a darker color. That jar originally was the same color as the second one, being more of a pale greenish-yellow tint. The one on the left was stored in a flammable cabinet, whereas the one on the right was left open in a darkened garage area, not subject to direct sunlight. I point this out because it's important to identify the fuel by color when sumping from the fuel drains, and I've never seen 100 low-lead darken with time. One other notable item is what happens when G100UL is left in an ASTM-rated epoxy bucket. It leaves a brown ring, which seems to be permanently enshrined in the epoxy. In this section, I'm going to talk about some affected aircraft, starting with the Beach Bonanza, followed by a PA-32, an elusive Cessna 210 that was rumored to have leaks last fall. I'll touch on the affected Cirrus, and then go into some additional testing regarding the Cessna 421 fuel selectors. One of the more notable updates about users of unleaded fuel comes from San Martin Airport. This pilot has consumed 531 gallons of G100UL and recently ceased utilizing the fuel. At the time of his ceasing usage in March 2025, he had burned close to 7% of all G100UL sold in California. Let's examine his detailed report. The South County Airport Pilots Association links Paul Marshall's report on his experience with G100UL and his beach bonanza. He had some positive experiences and also some negative experiences, which are highlighted here. He points out several items that were of concern: paint damage, a potentially clogged injector due to the fuel, and a mysterious varnish on his oil dipstick. A couple other things to highlight. In addition to the clogged injector that he says was over a portion of Mexico that he didn't want to experience an engine out, he had some things that came up at his annual inspection. There was a varnishy substance on his oil dipstick, which is near the oil breather exit, which suggests there's some form of material buildup. And you can see that noted here. They had to clean it off with a solvent in order to remove the material. He did note that this was not normal prior to use of G100UL. You'll see the staining here in the bottom of his fuel vents. He did also note that on the upper surface of the wing he had some staining in which he had actually applied the recommended ceramic coatings. It damaged some stickers on the aircraft, and he also questions whether some muffler damage may be related. Notably, his oil report from Blackstone did indicate there was less wear metals in the oil, which is a positive aspect of the use of the fuel. But in his case, he just couldn't overcome all the other adverse effects he was experiencing. If you're interested, I've linked Paul's report down in the video description below. I believe it's certainly worth the time to read through his experience. I'm pivoting back to an aircraft I previously covered in January. This is a PA-32 that had a leak on the left wing from the fuel sender gasket and had eaten some of the paint in the lower left wing area. Recently, the right wing also leaked from its fuel sender gasket, and it has even more paint deterioration on the aircraft. Many of the Piper series aircraft have a fuel tank that's a portion of the leading edge of the wing that can be removed. The fuel sender gasket's at the back towards the spar, and in this case, as you can see, it leaked, and then fuel drained down the bottom of the wing along the spar area, and has damaged several sections of the aircraft, far worse than the first time it occurred. My understanding is that these gaskets on the fuel senders of both wings were not that old, because the owner had recently had some avionics work done and installed new electronic fuel senders. Again, it's another example of paint being deteriorated when a leak occurs with G100UL. This obviously raises a valid question of why did two fairly new gaskets from both wings leak separately over time with the introduction of a new fuel. The only staining noted is brown in color, which is typical for G100UL. Several weeks after the Reed Hillview G100UL STC day in November 2024, rumors started swirling around the airport regarding a Cessna 210 that had some paint deterioration and leaks. In March 2025, I finally made contact with the owner of the elusive Cessna 210. The owner indicated to me that he had topped the tanks off after the STC day, did not run the engine or fly the aircraft, and came back a week later to a leak and paint deterioration on both the aircraft and the floor. And as you can see here, it's dripping out of the boost pump overflow hole, and it did a number on his epoxy-coated floor in the hangar, along with damaging the bottom of the aircraft. This situation is interesting because the aircraft was only topped off with fuel, and the engine was never ran. It's likely that the heavier constituents of G100UL settled to the lowest point in the fuel system. After all, G100UL is said to be heavier than 100 low lead. I think it's therefore logical to question whether the introduction of this fuel pushed a seal in the boost pump, likely an O-ring, over the edge, and it started leaking. Unfortunately, the owner sent the boost pump in as a core, so it's not available for inspection. And since much of the discussion on the internet is about possible poor paint jobs and bad paint quality, I'll note that this aircraft was painted at T&P Aero Refinishers in Salinas in 2014. They're a really well-respected, high-quality paint shop. And digging into the paint topic further, one wonders what type of paint is least affected. I've only seen GAMI publish photos of white Bonanza panels. But metallic paints, in my opinion, have had the most spectacular paint deterioration when interacted with G100UL. Take, for example, the affected Cirrus, which has a metallic silver paint job and major paint deterioration. And I'll note that the Cirrus was recently patched up and flew to a Cirrus service center in Grass Valley for repairs. This is also evidenced by the metallic Mooney oil doors that I tested a few episodes back. They had some pretty spectacular reactions to the fuel. Some research was recently presented to me that suggests that the high boiling point item of G100UL, namely M-toluidine, reacts with metals. in a way that would suggest the paint deterioration I've seen on metallic paints is in line with that theory. And since some element of copper might be in a metallic paint system, it makes me wonder if there's a reason the copper strip test, typical with an ASTM test standard, is not included in G100UL's fuel specification. In my previous video, video 4, I showed how the local Cessna 421 that sparked all my research was having an issue with the right side fuel selector valve. We went and took a look at the fuel selector on his right-hand wing, and while trying to exercise the fuel selector through all its positions, it was clear that there was resistance in at least one position and not functioning properly. So curiosity got the better of me, and I acquired 2 cores of Cessna 400 series fuel selectors, just like the Cessna 421 have. It is a shuttle valve style. The O-rings are actually not always constrained, and I wondered what happens when these O-rings swell in different fuels. So I bench tested the theory. This article in February 2017 Twin Cessna Flyer magazine does a great job of explaining the fuel system in a Twin 400 series Cessna. More specifically, it has a cutaway that illustrates the operation of the shuttle-style fuel valve in the Twin Cessna aircraft. What I'd like to highlight is that in either the left selected, right selected, where you crossfeed, or left engine off position, several of the O-rings are left in unconstrained positions of the fuel selector valve. This means the O-rings are in an open volume and free to swell. What I'm theorizing is that if an O-ring is left in the unconstrained position and exposed to fuel, it's going to swell beyond the limits and be damaged when the shuttle valve is moved. So, I wonder what the O-rings will do if they swell in this fuel selector. I took identical MS-29513 O-rings and placed them in containers with 100 low lead and G100UL respectively. And these are the results after a day of testing. On the left is the O-ring and 100 low lead. Middle is a mix of 100 low lead and G100UL, about 50%. And on the right is straight G100UL. The results weren't much of a surprise because they're in line with my previous O-ring test. Shown here is the volumetric change in the actual physical volume of the O-ring. 100 low lead gaining about 4%, G100UL and 100 low lead mixture about 32% gain, and a 63% gain in straight G100UL. After the release of my first video in December 2024, GAMI responded to me with the following statement, which they made publicly available via AvWeb. I'd like to highlight their response related to O-ring testing. They stated that their testing has shown that even though the older rubber compounds may swell in high aromatic fuel formulations, they don't deteriorate. This swelling has no negative impact on their ability to seal, and in some cases actually improves the mechanical sealing action of older rubber seals. That might be fine and dandy for static applications, but we're talking about a dynamic O-ring application here with the shuttle valve. And going back to Parker's O-ring handbook, they talk about general guidelines for limits of swelling and volume change of O-rings, stating that static seals, a volume change of 25 to 30% can be tolerated. However, they further go on to say that a maximum swell of about 10% should generally not be exceeded for dynamic applications. And if you go back to my recent volume change tests, we see up to a 60% increase in the volumetric swelling of O-rings in G100UL, which far exceeds the 10% that Parker recommends as a guideline. I then moved on to rig testing this theory, installing new MS-29513 O-rings and testing both straight G100UL and a mixture of 100 low lead and G100UL. I set up the rig with vinyl tubing so I could visualize the fuel and note any debris in the system. I installed new O-rings on the shuttle valve and then measured their OD to ensure they were not out of compliance with the inner workings of the fuel selector. Out of curiosity, I took one of the recently swollen O-rings that wasn't subjected to G100UL and installed it on the center shaft of the fuel selector. Note here that the O-ring fits very sloppily and actually rolls right off of the shaft with little force. The theory is that if an O-ring remains in an unconstrained position of the fuel selector and is subjected to G100UL, it will swell excessively, and then when shuttled into the next position, the O-ring will either come off the shaft, be damaged, or cause a jam in the selector. Let me illustrate the fuel selector positions. At the top is the neutral position, which is on for the primary engine, off, which is pulled out on the lever, and bottom is crossfeed, which then feeds to the opposing engine. Note here in the center, some of the O-rings, as you'll see in the following videos and photos, are unconstrained within the fuel selector. I put a little bit of lube on the O-rings and reassemble the fuel selector. Here you can see the normal modes of operation on the fuel selector through its full range of motion. Take note that when the O-ring is visible through this port, the outer surface of the O-ring is completely unconstrained as it's in an open cavity. Here's the simple rig setup, and while I could have rigged typical aircraft tubing, I used vinyl tubing to be able to visualize the fuel and see if there's any debris in it. I then cap off the connections once full with G100. After letting the fuel selector sit overnight, I came back and exercised it through its full range of motion. Initially it was stiff going through many of the positions, and then freed up. I then opened the fuel selector up and noted that several of the O-rings had sheared or broken. I want to point out that I did not rotate the actuator shaft during normal operation, but only for illustration here. Now visible in the tubing is a portion of an O-ring, only 1 day old, and hopefully to be caught in your fuel system's filter. I then drained the fuel out of the fuel selector, and here's the O-ring that was in the clear tubing. Full disassembly of the fuel selector valve then followed to see the extent of the issues inside. The first thing I noticed is that all 3 O-rings that seal the fuel selector valve on the main shaft were no longer in place. This means that they were now debris somewhere in the fuel system, so I had to locate them next. I also noticed the main seal O-ring on this portion was swelled, as would be expected with my previous experience with the fuel and nitrile O-rings. Note that this particular O-ring was left in as I received it with the fuel selector. I wanted an additional data point on older O-rings. Looking inside one of the ports, I located the remainder of the O-rings that were just sitting freely in the bottom, nicely cut. At this point, one should be concerned that O-rings that were installed the day prior and subjected to fuel are so much swelled that they then get sheared off within minutes of the first usage. I decided to repeat the test a second time. I went through the fuel selector, made sure it was clean, there were no burrs or anomalies, and then set it up for take 2. After installing new O-rings, I filled the rig up with fuel, capped the ends of the tubes, and let it sit overnight for about a 1-day soak in fuel. I removed the plug from the fuel selector, installed a camera above it, and cycled it here for the first time after sitting for a day. The fuel selector initially was tough to move, and then freed up over time. And as you'll note here shortly, one of the O-rings soon disappeared on the shaft. Once the O-ring disappeared, the fuel selector actually got stiff to move and had resistance, and I suspect that was because a portion of the O-ring was binding in the system and then was cut on the next movement. Again, within several minutes of moving the fuel selector, it had dislodged the O-rings, as you can see some of the portions here in the tubing below. Disassembly of the fuel selector soon followed, and the results were in line with the previous test where several of the O-rings had been damaged. 2 of them had come off their respective positions, while 1 was still in place but heavily damaged, with chunks of it missing. Here's another view of the shaft of the fuel selector. You'll note the 1 O-ring that remains in place has several chunks of the O-ring material missing, whereas the other 2 are basically off the shaft. This would be a picture of the debris that you'd probably locate in your fuel system, hopefully in the fuel filter. Here's an image of the nibbled away O-ring under a microscope. You can see that 2 large chunks are missing. As noted earlier, I had acquired 2 400 series fuel selector valves, both of the same part number with slight internal differences. I rigged the second one to test with a mix of 100 low lead and G100UL. I let it sit for at least a day in the fuel, and upon actuating it, I noticed that it had stiffened up significantly. For this test, I had used the local 421's fuel, which I had drained out of it, which is around a 50% mixture of 100 low lead and G100UL. While the local 421's fuel selector is yet to be disassembled, I suspect that it has a similar issue going on within it, with swollen O-rings and stiffened movement. After minimal testing, I took apart the fuel selector and put the O-rings on it under a microscope. You can see in the following several videos that the O-rings were damaged and several portions had either been worn away or nibbled away on the O-rings. I find this unacceptable. It's likely that these O-rings would fail prematurely due to damage. Again, Parker's ORD 5700 handbook is really a great resource for looking at O-ring design and failure modes. Here, the issue isn't that this is an improper fuel selector design. It's that the fuel that's being applied to legacy nitrile O-rings is incompatible with that rubber, and the extreme swelling is going to cause issues in this particular fuel selector. G100UL concentrations of 100% were observed to swell O-rings in the Cessna 400 series selectors well beyond limits. Resistance to fuel selector movement was observed in both straight G100UL and a mixture of 100 low lead and G100UL. New O-rings subjected to about a day of G100UL exposure in situ were sheared in the first few cycles of the selector valve. G100UL concentrations around 50% were observed to swell O-rings in the Cessna 400 series fuel selector significantly, and upon movement in situ, nibbled off portions of the O-rings. I suspect the observed failure modes will be experienced with in-service applications of similar design. Significant questions exist about the ability for mechanics to replace BUNA-N or nitrile-style components with other materials in the field. I've been unable to locate any approved replacements for nitrile O-rings in the Cessna 400 series fuel selectors. Outside of specific manufacturer approvals, McFarlane is listed as the only other manufacturer with FAA approval for fluorosilicone or Viton gaskets and seals, and they do not list having them for the Cessna 400 series selector valves. The FAA has a VARMA program, short for Vintage Aircraft Replacement Program, but this is intended for out-of-production or hard-to-find parts on a case-by-case basis. So I fear that we're trying to venture into owner-produced parts for, quote, drop-in fuel. Wrapping this all up, I'll say while sales have slowed of G100UL in the Bay Area, aircraft are still having adverse effects, seemingly proportionate to usage. I believe the swelling of O-rings in the Cessna 400 series fuel selectors is a potential safety of flight issue that warrants investigation. Brand new O-rings should not shear upon first usage when in contact with fuel for less than a day. A drop-in replacement should not cause extreme swelling of aircraft components or require changes to O-rings and seals that are not approved by the manufacturer or any approved aftermarket parts. My observations appear to imply that currently in service nitrile components may degrade faster with introduction of G100UL, and thus could require life limits stated in an ICA. After all, Part 91 operations are on condition, and accelerated aging needs to be better understood. I fully realize that any product rollout has its hiccups, and there is never always a perfect situation. The replacement of leaded avgas is a unique challenge. However, we need transparency in this entire process. I've been discouraged to see blame attempted to be shifted to aircraft owners for, quote, improper maintenance. The question I have is why were all these aircraft seemingly okay until the introduction of a drop-in fuel? If there's a new standard set for materials or life limits, be clear and state it. And while I've done this testing on one particular fuel, I wouldn't hesitate to give other candidate fuels just as much or more scrutiny. Thanks for watching and have a great day.